And here we go. So let's get back. All right, so my question was, what is a difference between the blue sine curve and the red that is being transformed? What's one thing you notice?
Yesterday you said how the range, you can increase or decrease it.
Yeah.
And that's what happened here.
What's the maximum range we have in the minimum? The range is between?
Let's put
5 and negative.
5 and negative 5.
Yeah, right. You can see them both at once. So 5, negative 5 is our range. That's good. That's talking about the y, the variation between the y. Today we're also going to learn that that is the amplitude from our midline here. The midline cuts everything in half. And the amplitude is how far up or how far down to get to the crest and trough. Okay. What's something else people are noticing? What does he see? Good.
The blue line is moving.
Say, which one's moving?
The blue one
The blue one?
isn't moving. It's not.
Isn't. Good. I had the exact opposite. Wanted to know about that. Okay. The blue one's stagnant. That's showing how the red is our transformation of the sine curve. So we're just seeing that. Anything else in common between the two curves? Yes. Both start at the origin. So there's no translation, horizontal translations. One thing we're going to look at today. And we looked at the period is how many cycles you get within 2 pi. So how many cycles do we have? We have 1. So the period is 2 pi. That's how long it takes to get from the start to the finish.
The points where the two graphs intersect are always staying the same, even though the other x value or y values are changing.
Yep. So we have in common they're all the pi values moving up. We only go to 2 pi usually with the unit circle, but you can extend that forever. You can go to 100 pi. That's great. That's great. All right. Any last ones? Did anybody see my 3D challenge? You see it? Yeah. Who can see it? Curious. Spatial. Nice. Nice. You see it now? So imagine that this is when it's totally facing you, and now it's rotating.
Yeah.
And then you're looking right down it, and it's rotating. You see it now? If this was actually a z-axis coming out, you would be able to graph that with 3 variables. If you were able to graph it, there is also, let me pause it, because I'm going to show you one thing that you do when you get to BC, actually. Sorry if you wanted an AB. Almost. You can rotate about the x-axis. So if you rotated this around, and this would rotate around, so the rotation that we were seeing, we can actually create a solid vessel by rotating that around. If I got a parabola and I rotate it around the z-axis, it becomes like a weird base that is kind of has corners, and it's like rounded at the top and bottom. If you can visualize that, the math needed to accomplish that is integral, calculus with integrals, which is BC, or the second semester when you get to college. So that is just, I mean, if you imagine everything that's ever been 3D printed has an aspect of, they could scan an object, but they can also work it out from scratch using a bunch of formulas. I'm going to rotate this one 360 degrees. I'm going to take out this portion from this polar coordinate. So we need polar coordinates to do a lot of that too. We're going to see that in 2 weeks, polar coordinates. They're a lot of fun. Okay, that's good. Y'all see these? Okay, so does anybody make music or do any sound engineering? Cool, right on. So you know that if you record it, say if you recorded the blue was your guitar track. You recorded it, and it wasn't quite loud enough. So we see that if we, let's go the other way. Get back. Faster. There. Keep playing. If we were to bring it up to here, the sound amplitude is just how much volume you're giving to the track. So you record like 10 tracks, they're all in your master mix, and then each one of those you can mix as well and get into like the sound of each track. So this would be turning up your guitar, almost 5 times as loud. So maybe that's like at a solo part. Actually, never go 5 times as loud. That's kind of wild. Maybe twice as loud. We go back to 2. Then we could see it. All right. Does anybody know what noise cancellation headphones are?
Yes.
How does that work?
It takes up
Cancels the noise.
I love it.
Yeah.
You see this right here? If the blue represents the wavelength of the sound with all the frequencies involved, and the red is the noise cancellation component, what your headphones do is it assesses the blue line with the formulas we're using. It then creates the reciprocal of it, or sorry, the inverse of it. So it was at volume 1 here. The same frequency of the sound has been contorted so that it does the opposite of the sound. So instead of being a sound that's at 1, you have a cancellation of -1 of the same sound unit. You have to manipulate the waveform. So if you had like a song and it just looked like, it was like this, right? Each peak, your headphones would assess how far is it how far to this point. And what I'm going to do is invert the sound created by that peak, and I'm going to make it go down at that point instead. So it actually contorts the sound. I don't even know what it would sound like to just hear the cancellation, the negation kind of sound. But that's how it works. We have peaks and troughs, and they're going to be canceled out. This is a trough, so we're going to cancel that with a peak. And it works so on like that. Yeah, you know anything else?
Is that like almost like compression?
Compression may be a part of that process, but I don't think that's exactly the same. I'm curious what you think. So when we get to the 4 aspects, I want you to find compression in there. Just you. What else? That's good. So let's bring this back to 1. If I look at this at 1, here is the new sine. This is the new sine formula that we're going to be using. If my A is 1, right, then it's just y is equal to sine. If my B is 1, then it's y equals to sine with some aspect here. C is 0, so essentially all this so far would be y is equal to the sine of x plus B, that's 0. So all that you see right now is y is equal to the sine of x. We're going to manipulate these different things. So watch. Now I want you to tell me what's happening in this one. Oh, maybe we already got to it. What do you think? What's happening?
It's stretching.
Seizure. Stretching out. And then compressing it.
It looks like an accordion.
Accordion.
Like a slinky.
Yes.
Wow. You saw the notes before we're done. Perfect. So you look. Yeah, Andre.
It kind of reminds, well, looking at B, it kind of reminds me like a parabola, where like 2 points, one on negative and one on the positive side, have the same y value.
Okay. So like a translation or across the y-axis. Is that what you're saying?
Yeah.
Okay.
They look similar areas.
I like how you're looking at that. And essentially what we're looking at, let me pull it and stop it at a moment in time when we can assess it. Oh no, it's towards the middle. I want it here. Okay. So we know that the blue is the sine. Wait, I want to get it perfect. There we go. We know that the blue is the sine curve. And if I start here, a full sine curve is completed at 2 pi. Now how many of of the red sine frequency, or sine wave, are we having between here and here? How many do we have to do? 1, 2, 3, right? So our frequency is 3. The frequency is just how many times does the wave repeat between 0 and 2 pi? Every time. Okay. So essentially this is compression horizontally, in and out, and I don't know how that's related to compression audio engineering. So think about that one. Yeah.
Is D always going to be equal to the amount of things that we created? So we're going to make it 4. We're doing 4.
Let's see. I like to explore it. No. Yes. All right. So again, the blue, 1 to get to 2 pi. There's 1 cycle between 0 and 2 pi. How about here? 1, 2, 3, 4. Okay. I want to prepare you for the next bit, which is asking for the period. The period is saying how long to get through 1 cycle of the wavelength. 1 cycle is between here and what? There, pi over 2. That's pi. That's probably pi over 2. Okay? So essentially, if you know the frequency, how many identical waves do you see between 0 and 2 pi? Right? If you saw 100 waves, what would it look like? It'd be like what? Between 0 and 2 pi would be 100 times. So do you agree that if it takes 100 times to go from 0 to pi, that each individual cycle is really small? You agree with that? So if it takes 100 to go from 0 to pi, 2 pi, 100 times, to find the period, how long for one? I go 2 pi divided by 100. Does that make sense? 2 pi is that distance we looked. There's 100 there, so to find each one, I'm going to take 2 pi, divide it into 100 parts to see how much one is. That's the hardest part of the lesson. Going from frequency to how long is the period, how much for one cycle. Okay, so we know this one. We've kind of like established it. It's kind of like compression. Look at what happens when it goes to 0. What do we end up with? Straight line, right? So if you look at the equation up here, right? If this is 0, my entire angle theta is gone. You see? So what is the sine of 0? Think about it. Start on the initial side, we're rotating around. What is my y value when I have 0 degrees or 0 radian? It's 0. So you could see, really, if you use your Desmos calculator even on your phone, you could double check all your work. This is the master. And with cosine, it's just cosine there instead. It's the same exact formula. All right, let's get back to 1, though. All right, C. What's happening now? Do you need hot drop? Too many stale Twizzlers. I can't give them away if they're stale. I just have to just pass it.
Clearly you can.
Clearly, I can't give them away as prizes. Yeah. What's happening here? Somebody give me some input. Yes. Transformation along the x-axis, all it is moving. It's lined up right there. And within waves, we call it a phase shift. Phase shifting. This also tells us where our starting point is going to be. So if I'm right here, if I've had a phase shift of pi, then I know that my initial wave is going to start there at pi. That tells us the starting point. Basically, wherever you move it, we're going to start from that point as well. It's all going to come together. Don't worry. 0? You guys tired?
No.
Yes.
That's a trick question.
Really what? I'm not motivating you enough?
No, I'm just.
I can do all, try anything, it's not going to work. Push everybody.
Like every play.
Oh, that's next. We'll do D first. What's happening here? That'll motivate you. Yeah.
Translation.
Yeah.
Down.
Translation what? Horizontally now. Up and down. Okay, the moment you've been waiting for.
Whoa.
Let's close this so we can see all of it. Yeah. I can make it so just
Looks like
those
a DVD.
because that's the that's our D, C and D value. Let's see what happens. Watch. I'm going to go ahead and pause these. Now look what happens.
No,
We're going to make everything go.
DVD, but
We're going to make everything go way fast.
yeah, it has to hit a perfect chord.
Just because I like to see what happens when I push buttons. Wow.
Where's the center point? I can't tell.
It's always moving. In fact, you can kind of see it's like. Wait. No, I can't do it. Because they're not matched up. I pushed all the slides at different times, so it's kind of doing like a. It's not exactly a perfect circle. Might be an ellipse. Ooh, that would be fun. No.
Just like if you try one of the curves, it's where it's like diagonal.
Right. Starting the starting the C and D values at different times would get a slightly different path. I was just thinking how to, like, your test would be make a path like this. We won't do it. Oh my, sorry to overload the brain.
Yes.
All right. Let's go ahead and pause. Here we go. Okay, we are back. And now this board is really full, but it really has 4 key elements. The 4 key elements are showing how we're going to modify our normal sine curve, right, in order to make the amplitude larger. So bring the trough and the crest away from each other. We're going to have a compression aspect that also makes us have more than one cycle between 0 and 2 pi. We're going to have some shifts where we shift left or right. And that is mainly it. The midline's a real easy idea. Okay, so let's look at this also start up. This is going to be the main way that we are going to graph our trig functions for cosine and sine. If this was for cosine, you would just have cosine here instead of sine. That's all it would be. The values would mean the same thing. You would just have to know what the standard for the cosine looks like, just as we know the standard for the sine. So if I look at this, in this case, my A value, my amplitude is 1. 1, right? It's not there, but it's always, in essence, for the standard sine curve, it's 1. Okay? My B value, the frequency, is also 1. Frequency is just saying how many times do you cycle in order to go from the 0 to the 2 pi, or any increment of 2 pi. Pi over 2 to 5 pi over 2 is another example. Let's see, C. We don't have anything connected to the x, so there's not a translation in the horizontal way. And we don't have any D value right here. So essentially we do have A, B, C, and D values for just the regular sine curve, but what we get is a regular sine curve from this. We're going to be manipulating that using those 4 elements. Stretching, compressing, moving up and down, making the amplitude 1. Okay, so when we look at this, it's pretty easy to see what the midline is. Step 1 is going to be finding the midline. Okay. Now you tell me, when I am, there's a line there already, but this is obviously not the midline, right? The midline is the center line of the function. It's always expressed as y is equal to something, because all horizontal lines are y is equal to something. So what is my midline? Give me a y is equal to what? Y is equal to 0, because here would be y is equal to 1, y is equal to -1. That does show our minimum, our maximum, and our minimum. But the midline is just what they balance in between. The amplitude is always going to be the same going up as it is going down. Okay, so midline is where we start to graph these things. You can see that tells you just like where is it going to be, how much up and down are we going to be translated. The next bit, if we go down, so cleverly numbered to number 2, horizontal shift. So this is where we have our starting point. We're going to find our starting point in this. Does sine of x have a horizontal shift? No, it doesn't have a horizontal shift. But if it was, let's do a hypothetical. And this is where I want to bring up something kind of important. What if it was x minus pi over 2? Maybe just rewrite that whole thing on another, like underneath those notes. Y is equal to x minus pi over 2. And I want you, for 20 seconds, talk to your neighbor. What do you think would happen to the graph with x, or sine is equal to sine times x minus pi over 2? Talk to your neighbor for 20 seconds first. So tell your neighbor that. Are you talking to me?
No, because in the equation
Okay. Let's see. All right. Who's got an idea about this alternate here? If it was x minus pi over 2, what would we see as far as a shift? Because we're talking about, with that, the horizontal shift, the phase shift, to the right or left. Where is it going to start? Where's our starting point going to be instead of at 0? Where should it be? pi over 2. Who thought it was at negative pi over 2? It's possible, right? That's like a crux. You might think that. Here's one way I like to explain it. When we did the vertex formula of the parabola, this is probably where it was explained, I hope, last year for some of you. If you're in my class, you know too. But the analogy that I give for this, see if this works for you. If everything in black, which is the key operations and function of this graph, if everything in black was, outside my room, it was like pieces of metal welded to the wall. Everything, the y, the sine, everything that is going to be stagnant, x, minus, all that is welded to the wall, right? Then if I plug in a c value of pi over 2, I know I'm talking about a positive shift of pi over 2. This is welded to the wall, remember? So if my c value is negative pi over 2, then what will we see in this parenthesis? X plus, okay? So if that helps you a little bit, I like to think of these as like foundational formulas here to graph the trig function. So this is just standard form of the sine function, and that tells us that that negative is a part of the function, okay? It's not saying if it's negative pi over 2, we're going negative direction. So just keep that in mind. Make the arrows nice. Okay. So far, the two things we've done, midline and horizontal, would you be able to graph those things, pulling from information? Probably? It's okay? Okay. All right, so next we're going to talk about, first, you guys know what a quince is? A quince? It's a type of fruit.
Oh.
It's the only fruit within its genus. You guys know what a quince is? It's like green. Okay.
Wait, I need to
Did you know that they are high in vitamin C? It's pretty good, huh? I heard there's actually a place in town you can get a free quince C with the vitamin C in it. It's for you, Evan. Come on. Free quince C. Free quince. Quince. A free quince has vitamin C. Yeah. Quince is a real fruit. I don't know, but a lot of fruits have vitamin C. I was forcing that pun for Evan. And
You really tried, man.
I did. Oh no, I don't need laughs. I don't need laughs. See, the key to a good joke is also doing it so poorly that it's you get embarrassed for me and you clap.
Well,
So is free. Come on. Puns are based on
you
the
have
sounds.
my respect and gratitude.
That's like
You
11.
deserve a Starbucks.
I will eat it after my lecture. That had absolutely no educational value. It was for my entertainment, and I had a great time. So congratulations.
We love it.
I
I like that was good.
That's yellow.
Isn't bad.
But I think you should stop midlining the puns.
Right. Puns are amazing.
You should stop
Midlining.
Ooh.
Uh-huh.
Okay, let's take a deep breath and leave the puns behind. Let's go back to frequency. Frequency is just telling you how many cycles we get within 2 pi. So again, it could be between 0 and 2 pi. It could be between pi over 2 and 5 pi over 2. It can be any of those. Okay, not 5 pi over 2. 9 pi over 2. No. 5 pi over 2. Regardless, this is just looking at how many cycles between in an interval of 2 pi. So how many times do you see the same curve and the same repeat going on? So I want you to think about this. If my frequency is 100 waves between 0 and 2 pi, are those really big waves or really compact small waves? Can you visualize that? Think of like 0 to 2 pi and 100 little, 0 to 2 pi, 100 little waves within that. If I wanted to find how long, what interval each wave fits into, would you agree it's going to be a small amount? If we have to fit 100 in there, each is going to be really small, right? If I have 100 waves stacked in there between 0 and 2 pi, how could I find out the length of each wave? What could I do? 2 pi, that's how much you have to see how much each is. If it's between 0 and 2 and we have all these waves, 100 of them, then to find how many or how length of each one, we'd go 2 pi divided by 100. That's called the period. 2 pi divided by the frequency gives the horizontal distance before the y values repeat, or before the cycle starts over. Okay. That's probably the hardest thing. What I just said right there is the hardest thing. So how do we feel about just that idea? We have 100 waves, thumbs up, sideways, down. To find out how the length of each, we divide it. Good, good. I hit this. All right, so that's frequency. Number 4 is a little bit tricky. Jeez, darkness.
It literally.
No, it's something way spookier than the clouds.
Oh, did you have to visit this?
Sorry, it's not spooky. Give us a little light, Dan. All right, vampire children.
That's good. I have a spot.
Bring it back. Forget about the light. Bring it back. Number 4 is the toughest one up here. Number 4 is kind of tough. Number 4 is really, the amplitude is just the distance from the max to the midline. So we have this as our maximum to the midline. Now, if you don't have any information given on the graph, you can find it from scratch. If you look at this, what is my maximum of this graph? The maximum at the crest? 1. 1 minus what is my minimum, including the negative aspect of it? It goes down to? Negative 1. So what's 1 minus negative 1? 2, because we add it. What's 2 divided in half? 1. Now, this seems very obvious, but what if this thing's been translated up? What if we have different information that we're given for the minimum max? Maybe you're just given that and a few other details. So based on what you're working from, you may need to use this. Otherwise, if you're looking at the graph, you can just see where the midline is and how far to get up to the crest. That's going to just be your amplitude. Okay. Who feels ready to try to graph one of these things? Feel ready? Okay, good. We're going to bring it back over here. All right, let's stay focused for this one. This one right here. All right, I put the graph up here in color code, and I also put a basic graph here starting from 0 at the origin, and I just put some radians in there. Okay. So first off, use the map over there to tell me what are each of these arrows talking about. Let's do it in the order we have to break this down. What is this one right here? Midline, watch. Midline. Perfect. So if I'm doing the midline and I'm keeping my colors here, I'm going to go to 4. 1, 2, 3, 4. And that's where I'm going to put my midline. See? We already know where about we're going to see it. That's almost good. Number 2, the horizontal shift. Do we have a horizontal shift up here? What is our horizontal shift? So this is our horizontal shift. And this also tells us our start point. Start point. The horizontal shift, wherever it's shifted, that's going to tell you where the start has been shifted. Has it been shifted to the right or to the left? Right. So we go to pi over 2. That's our start point. See, the shift was over pi over 2, so that's just where we should start. Let's see, what is the frequency? How many times does the cycle repeat itself between 0 and 2 pi? 2. So this is our frequency. And what I'll say about that is, if between, this is really a distance of 2 pi because it's been shifted over, right? If I have to make 2 waves fit within this, approximately how far would one wave take before it repeats? So watch. I'm going to go ahead and go from here, and I'm just really breaking this in half. 5 pi over 2. This is 3 pi over 2. This is pi over 2. So I know that we're going to start here. It's going to start here. It's going to end here. So essentially, the basic would be like this. You see, that's 2 fit. The frequency is 2. 2 of them fit between 0 and 2 pi, or that interval, no matter where it is. So what I'm going to do with this is actually just put my starting points. I know it's here. I know I'm going to end up with a starting point there, and it would repeat to there. See, that's where we're going to go across the midline. Those are all my midlines. So it's probably going to go it's going to cross again, but the starting points. It's not whenever it crosses the midline. It's one wave, one period, another, and it takes two. The frequency is 2, so we know we're on track. Okay. What's this last thing? Okay, amplitude. So let's look at what we have here. We have an amplitude of 1/2. So if I'm looking at this, if my amplitude is 1/2, remember amplitude is equal to 1/2 times the minimum, times the maximum minus the minimum. So let's go ahead and do that. And this is max minus min, but really we can find this without doing much more, because 1/2 is equal to 1/2 times what? 1/2 times 100. So we know that because we have a 1/2 out there as the amplitude, that we're going to end up with a amplitude of 1/2. Actually, I need to make this graph a little different for you guys. I do. It's going to be really small. But we know the amplitude actually, we know it right off the bat. We didn't even have to do that portion. We knew it was 1/2, so I know that is from the midline to the crest is going to be a measurement of 1/2. And this is going to get kind of messy here. Let's do it. That's going to be the lower range. Upper range, this is going to be the lower range. You see how I did that? Actually, this is only helpful for working backwards from this information. It's not that type of problem that we're facing for this lesson. So if it's 1/2 here, we know that the amplitude is 1/2 from the midline to the crest, the midline to the trough. Now we have every bit of information. Now we can graph it. So I know that between these points, there's an entire wave, an entire cycle. So watch what I'm going to do. About in between them, I'm going to hit down and go up. That's 1. And we go up and go down. That's 2. That's what we were asked to graph. This would continue indefinitely, but we were just going between these 2 segments. That's mainly what I'm interested in. A 2 pi interval. There's a lot to this. But do you feel like one step at a time, it's doable? Okay? Is this? Okay, good. I want to do the first problem in the classwork with you and actually record it. So go ahead and get out your workbook, page 91. 91 in your workbook. This one goes from a graph to labeling all these aspects. Inception.
Number 1.
Let's look at number 1. These are not drawn perfectly, so I want to get your input for it. Look what we're finding. We're just trying to find the period, the frequency, the midline, and the amplitude. So we're finding our 4 things here. We don't have to put it into a formula, but since you guys are honors, I want you to try to put it into a formula. Come on now. There we go. That's a little better. Let's make it bigger. All right, I'll get my lasers. Where's my laser? All right, first things first. We are going to find the midline. Am I at the midline right here? No, obviously not. Too far down. Where's it going to be about? So one way to know what's the midline is look at the crest. Where's that at? 2 approximately. Where's the trough? -4 is -1 right in between them. It is. So let's put the midline as -1. So you're just labeling on the side. The midline is -1, and that would be that value that goes out here. So it would be all of that -1. Next, let's find the horizontal shift. We will assume that this is a sine curve for all these problems. So if I'm at -1, what does the sine curve do first? Does it go up or down? Starts at the origin, goes up. So have we had a horizontal shift at all?
No.
Because if it was starting at the origin, it would go up, then down, then up, then down. So if we're starting at -1, it goes up through the midline down the trough, up, midline down the trough. Okay. So we're going to say that it does not have a horizontal shift. So there is no value within the parentheses here. It's just x. It's not x minus anything. It's x minus 0. There's no horizontal shift. Because we know at our midline, that frequency starts just like a regular sine curve. We're going to assume they're all sine curves. All right. That's what the lesson is. All right, what's next? Frequency. So we go from 0 to 2 pi. How many full cycles do I see between 0 and 2 pi? Let's see. It goes up, down. So that's one whole cycle right to here, right? Up, down, 2. So you know your frequency is 2. So think of that. You've taken your 2 pi, you've cut it into 2 parts. That's how we're going to find the last thing. Actually, did they ask for the period or amplitude? What did they ask for? Both?
Oh.
Okay. The period, since we did frequency, is easiest to do here. So if I'm trying to find the period, basically I'm asked, first, what's the frequency? There's 2 full waves before we get to 2 pi. So the period is how long each wave is. We take 2 pi and we divide it by what? 2. What do we get? Pi. So we get pi for the period. One whole cycle takes pi radians to get through. And last, the amplitude's really straightforward. Watch. -1. Amplitude is from the midline up to the crest, or midline down to the trough. What do we have? 3. So I think if we went through this, we'd have y is equal to 3 times sine of 2x. That's it. You see how I put those in there? This is 0. There's no horizontal shift. We have an amplitude of 1.
No,
Right.
the midline is -1.
Oh, so it's from -1, the midline to the top was 3. That's what you guys said before, right? Okay. So A is equal to 3 times the sine. The frequency is 2, so it's 2x. This is 0, that's 0. So it's 3 times the sine of 2x. Yeah. Keep thinking. Hey,
When would you know when there's a horizontal shift?
I would know there's a horizontal shift because if I'm assuming these are all sine curves, right? This is the start, and if it was the origin, I know the sine curve goes up, and it goes down, and it comes up again. Okay. So if I looked and saw that one of my, if one of them started here instead, and that's where it was going up, then going down, right? You follow the same general idea of where does the sine curve start, and you could shift it over to you have to make that judgment. Because it's going to probably keep them going in either direction, right? It's going to go in either direction. So you basically have to look to see, I know that wherever my midline is, the sine function always starts by going up from that midline and then back down. You got to know a little bit about the parent function. That's why we know about sine. So let's see. I think maybe the next one, I'll just pull it out to see if we can try it and see if that has a shift. Gene?
I have 2 questions. One is, I was looking ahead, and 5 is cosine, so that's the same thing.
Same thing?
Okay. And then,
It would be cosine here, that's it.
and then also, for this one, I just did the midline. Would it be -1?
It is negative.
Yeah, so D would that be, so it would be y equal to 3 sine 2x minus 1.
-1. You're right. So the amplitude is 3 times the sine of 2x minus 1 is on the outside. You're correct. Thank you for solving that for us. That was my error. All right. Any other questions coming up? You want to just, the last 5 minutes here, I'm just going to give you time to work on it, but I want to show that phase shift. And I think this one has a good phase shift. This one right here, number 3. If this is a sine curve, we know that it does not start at the top at a crest. It starts right here. Right? It starts right here. The sine curve would then go up, we go down, we go up. Yeah? Okay, good luck.
Thanks.
So if I make my midline, I look and see that this point over here is acting more like a cosine. So I would look to see that my Well, I can almost put the cursor on it. This is where I'm going to start, right here. Right? Because that's the first point where I can get a real normal-looking sine curve going. It goes up, then goes down. So Carson? All right. So this would be, in this formula here, it would be x minus pi over 2. And then you would find your frequency from pi over 2 to, 5 pi over 2. Okay? So you're going to notice it. Remember, in this case, we're doing, good luck. We're doing sine function. If it was cosine, you could say there's no phase shift. Second level. We'll get to that when we see cosine and remind you. All right, give it to me. Thumbs up, sideways down. Give me the real deal here. Okay. Okay. So we're averaging here. Good. All right, work with a partner. Try to do the graphs real quick. And to those watching at home, those puns were a gift. Treasure them. Frequency, as in vitamin C.